Topic 11, Measurement and Data Processing by Alexis Hyatt, Jason Glover, and Eric Curl. Random uncertainties are caused by the limitations of the measuring equipment and other uncontrollable variables within the experiment. For example, when measuring mass using an electronic scale, there are variations due to currents in the room. When cutting anything, there could be slight variations in the weight. Systematic errors occur due to the equipment or the procedure result in lost accuracy. For example, a beaker that is not well insulated, so heat escapes cause the temperature to be less than the actual value. When you're measuring from a graduated cylinder, you measure from the top of the meniscus instead of the bottom. Precision refers to how close the repeat readings are to each other and the mean value. Accuracy refers to how close the value is to the true value of the measurement. For example, if you shoot an arrow at a target and hit almost the same spot each time, then there is precision. If you're hitting a spot outside of the middle, it is not very accurate. The effect of random uncertainties may be reduced by repeating the measurements to get a more reliable mean value. Also, uncertainties can be minimized by careful design of an experiment. However, random uncertainties can never be completely eliminated. We can give an indication of the size of the random uncertainty by using the measured value with an uncertainty. The uncertainty of a measurement is half the smallest division to which you take a reading. For example, if the nearest division is 0.5 millimeters, half of that is 0.25 millimeters, or 0.3 millimeters, so the uncertainty would be plus or minus 0.3 millimeters. With sig figs, we count from first non-zero digit. We count any zeros after the first non-zero digit and after a decimal point. When there are whole numbers like 500, there could be 1, 2, or 3 sig figs, and this can be avoided by using standard form with different values. You match sig figs with the value with the lowest number of sig figs. Percentage uncertainty equals absolute uncertainty over the value times 100. For example, if you have 0.257 plus or minus 0.005 centimeters, it would then be a percent uncertainty of 0.005 divided by 0.257 times 100, which would then equal 2%. Absolute uncertainty is the percentage of uncertainty over 100 times the value. For example, if you have 0.518 plus or minus 1%, absolute uncertainty would be then 1 over 100 times 0.518 equals 0.005. When quantities with uncertainties are added / subtracted, absolute uncertainties are added. When quantities with uncertainties are multiplied / divided, percentage uncertainties are added. If one uncertainty is much larger than the other, the approximate uncertainty is a calculated result can be taken as due to the quantity alone. This graph shows a proportional relationship between the rate of the reaction and the concentration. Due to it being a straight line passed through the origin, the concentration doubles, the rate of the reaction doubles. The little one inversely proportional, and when volume doubles, the pressure is halved. Step 1. Choose scales and axes to make the graph as precise as possible and as easy to read as possible. Step 2. Independent variables on x-axis and dependent variables on y-axis. Step 3. Label axes with quantity in units. Step 4. Plot the points. Step 5. Title the graph. Line of best fit can be either a straight line or a curve and should represent the trend of the data. The points should be evenly distributed about the line. The slope, or gradient, gives us an idea of how much one quantity is affected by another quantity. Gradient equals change in concentration over change in time. In this graph, it represents the rate of reaction